This is how we denoting the steady state in the following, right? And this here is our original bubbles. And again, note this is all approximations. Okay. Good. This is just another one. So if you want, this is one of these prominent internet resources that actually I have used a lot when I learned this. It's pretty old already. You still find it, but I think so. Maybe that's helpful for you too, in case you want to check it out. Good. But yeah, I mean, this is just a technique. Right? So let me show you how you use it and why it's useful. Right? So this is our RBC model. This is the equations that we derived. What's the first equation?
It should be the Euler equation.
Exactly, right? So that's the household's consumption saving choice. What's equation 29? Optimal labor supply, right? So that was this other thing that we derived last week, right? Was 30. Capital demand, yeah, exactly, right? So this falls out of the firm problem here, this guy, right? So that's firm's demand capital such that the marginal product of capital is equal to the interest rate, right? 30 is just a corresponding thing for labor demand, right? How much labor do firms actually use, right, in their production? This is how they set it. What is this guy? That was this dynamic resource constraint, right? Where you basically say, by accounting, right, falling out of the production function and this law of motion for capital, right? So output equals consumption plus investment, plus we know the future capital stock, right, depends on our investment minus the depreciation, right? So this is this accounting guy, this is our production function, and this here is this stochastic process for productivity that I defined at the very beginning last week, right? We're basically saying this AT now, right? So this guy here is now follows this autoregressive process, right? So today's productivity depends on yesterday's productivity, plus what we call a productivity shock, right? Which is typically this random shock with some zero mean and some variance, which is fluctuating over time, right? We know that it's fluctuating. Or the agents in this model know it's fluctuating, right? But they do not know when exactly what shock hits, right? So that's the uncertainty here in this model. All right, and that's the thing that we want to work with, right?
What is this rho variable again?
That's the persistence parameter in the productivity process. So the idea is that this thing would be like 0.9. Then this determines how much does today's productivity depend on yesterday's productivity, right? If it were 0, then today's productivity would not depend on yesterday's productivity, but whatever, I mean, this thing is between 0 and 1, right? You have a certain, like, what we call persistence.
Could you think of it as the same as the depreciation rate, but for human capital? As in, like, the machines are worn out, but also the human mind is like losing its ability to solve tasks if you don't use it, or if you don't.
Yeah, it's not really like you're losing here, right? Because I mean, there's always new shocks coming in too, right? So what's happening here is basically that you're returning to the mean of the process, right? So this process, I mean, what this process looks like is really this thing that I gave you at the beginning, right? Sorry for jumping, right? It's basically this here, right? So this productivity process would be increasing and then it would be going back at some point, right? So that's what determines this process here, right? It has a constant mean, right? And we are always returning to this constant mean. And if you like, basically what it says is, let's say we had a boom period, right? Why is this not working well? Well, let's say we had a boom period, productivity is very high, right? So then this rho being smaller than 1 tells you that we're returning to the mean at some point. But also if you're below, you would also be returning, right? So it goes in both directions. All right, good. Good. Okay, so now if you actually want to solve this model, there's a few things that we still need. First problem being, I have these utility functions flying around, and I have here this production function flying around, right? So what exactly is U, what is F? And this is now the point where you actually need to make a statement, right? How will your functions look like? Because we want to make an approximation, so we need something to actually approximate, right? So this is basically what I do here at 35 and 36, right? So we're basically now defining functional forms for the utility function and for the production function, right? But I hope you will not be surprised, right? This is just log utility and consumption, and also like this labor supply, right? Or this utility of supplying labor. That's exactly what we discussed last week, where I talked for some time about this first elasticity, which is directly related to this parameter phi, right? So this is why we have this functional form in N, and 36 is just this production function, right? Neoclassical Douglas production function. So if you take these as given, you know what these derivatives look like, right? So you know what's the marginal product, the marginal utility of consumption, this utility of labor, and these marginal products of capital and labor, right? I mean, this is just what's falling out of the Cobb-Douglas, and this is just the derivatives of the utility function, right? So that's what we have. And I mean, again, right? The reason why we use 35 is just because then 37 and 38 look so nice and well behaved, right? Okay. So now we have this, right? So now let's actually do the log linearization, right? So I leave all the mass to Maria because she's kind enough to do this. I will just kind of focus on it. What does it give us, right? So we now take this Euler equation, right? That's the one that you've known before, right? This equation 35, this one here, right? And we now do the log linearization. And what this gives me is this equation 41, right? So this looks, I don't know, does it look similar, does it look different? It still is the same equation, but it's approximated in a linear way, right? So what you see here, first thing that has changed is we're going from these uppercase variables, right, CT, to these CT hats, right? That's the first thing that has changed, right? Here you have the CT, and here you have the CT hat, right? So the interpretation of these variables will also be different, right? In the upper equation, CT is actually in levels, right? Whereas the CT hat here is a variable which is in percent deviations from steady state, right? So that's the difference. You also have that for the other variables, right? AT becomes an AT hat, or AT plus 1 hat, KT once 1 becomes the KT plus 1 hat, and the same for N, right? So that's the first thing that has changed, right? But also the functional form looks different, right? But it looks different in exactly the way what you want it to be, right? 41 is a linear equation, right? So it's linear in the variables, right? So you, for example, see here the CT is clearly linear, this guy too. Also this here, right? You just have some parameters in front, but you do not have like an AT squared or AT to the KT. This is stuff which is not showing up, right? So this is a linear equation, right? And that's the whole purpose why we did this. It's still the same equation in the sense that you still have the same parameters flying around, right? So you have the B here, beta here, the alpha, there's an alpha here, right? So this is still all the same, right? But it's also in a way different, right? But you will see that basically what this equation will tell you, right? I mean, we've talked about the Euler equation a long time, right? Tell you something like, what if today's consumption goes up? That means something for tomorrow's consumption, right? And I mean, this trade-off is still here, right? So still relating CT to CT plus 1, right? This hasn't changed, right? We're just like, because of this linearization, it looks a bit different. Right? You also have, and I mean, that falls out of the log linearization, very often these steady-state values flying around, right? Which is, I mean, intuitively approximating around the steady state, right? And here you see that the steady states actually matter. Okay, so this is what the Euler equation looks like. You will actually see very often, and I remember that at the time when I've seen this model the first time, I found that often very confusing. Because sometimes in textbooks, depends a bit what textbook you open, you will actually only find these log linearized equations. I feel like this has changed a bit, but there used to be like really model representations of this model, also of the new Keynesian model that we will do next, that are only presented in log linearized terms. So there are some people who say that they find this easier. I have never found this easy. I always found this much more confusing. But you could be, maybe you're different, right? If you say, I find 41 actually easier to interpret than the equation above, I mean, that's to me completely okay. To me, that has always been a, I don't know. I just like the equation as it falls out. I just like it more compared to these approximations. But maybe that's also my personal thing. I don't know. But just to explain that, right? In case you open textbook and you just see these linear equations, that's what these people have done. Sometimes they don't tell you, right? But this is exactly what they did. Right? Okay. Okay. So this is the second equation. This is this labor supply equation, right? Same story, right? What happens? Change these bubbles to these hat guys. You have so these bubbles, these parameters flying around, but again, it's all linear, right? That's the beauty. All right. You also do this for the resource constraint, then you have this equation 43 falling out, and you do this for the stochastic process and productivity, which is luckily always very easy to do, because that's one of the reasons why we define it that way. Exactly. Good. But this is what you have. Right? But in the end, so just to say that again, this doesn't change anything in terms of your underlying model, right? The model that we have is still the same. The only thing that we did is now to approximate it in a linear way around the steady state. Right? And this is why these equations look different, and this is why you now have these hats flying around. But the underlying thing that's happening is still the same. Right?
Just a question about notation. So now it is not only KT hat, but a small KT hat.
Yeah, that's true.
Is this just because you change it that way, or because I remember if you have a small one, we have divided by labor and unit revenue.
Yeah, that's true. That was the case in Silver one. Yeah, that's right.
Okay,
No, that's actually here not the case. No, sorry, no. So it could in principle also be an uppercase K hat, but for some reason I've chosen the lowercase because I found that more. Oh, I don't know, but it's not related to this like the labor unit or pay efficiency. Yeah. Okay. So this is the log linearized model, and I mean just to say that Maria will do this step by step, right? She will show you, I think, probably next year, right? Because actually, right next week, there's no tutorial next week. So on Wednesday, I will actually be. Is that here? I don't know. I have to check, right? Maybe here or somewhere else, right? So next week, I will do the lecture on Wednesday, and on Thursday, you will not have a lecture, right? So which means there's no exercise class next week, right? So Maria will show you this year and next year. Right? All right. She will also do an announcement, right, on Blackboard, but just then you've heard it already, right? Good. So she will show you exactly, right, how you do the models to go from like the first equation to the second one, but actually the equation that she's doing that compared to the price equation. Okay. So now you've approximated the model. Right? This is the first step to solving the model, but you have not solved the model yet. Right? This is also one of these misunderstandings that I get from some of these textbooks, because they talk a long, long time about these log linearizations, whereas the actual solution comes now. And that's also one thing where I kind of hope I make that clear. Right? So these log linearizations are important, but it's not like they're the end of the story. And I mean, at some point, it's also true that, like in our applied work, right? So let's say you want to write a math thesis at some point, you want to actually do something with one of these models. I think it's super important that you know how these log linearizations work, but it's relatively unlikely that you will sit down and actually do this on your model, because what do we have now? We have computers that do this. Right? But I'm kind of this. Like, at least in to me, it has always been super helpful to have understood this once, right? What these computers actually do. This is kind of what I want to show you too. Okay. Alright, so let's now do this. How do we now actually solve this? And here, one of the big advantages is the model is still relatively small. Right? We have a representative firm, we have a representative households, that's basically it. Right? There's really not that much going on. There's not even any friction, right? It's in that sense a super small model. And this model we can actually solve by hand. And this is what I want to show you now. Right? Okay, so what we typically do is to use this method of undetermined coefficients, right? Again, this is one of these things you can Google, you will find millions of videos on how this actually works. But I will show you this in the context of the RBC model, right? So that's maybe a bit of a difference, right? So what is crucial to solve models is to understand what in your model is the state and what is the control variable. You may remember that I've actually pointed this out repeatedly during earlier lectures, right? Because it was also important at that point. Now it's crucial to know this, right? Because you have to understand this in order to be able to write down what your solution will look like. Okay. So what are our state variables in the model? The state variables is always like, as the agents in the model, they wake up in the morning, right, in the new period T. What is it that they have to live with, right? What is it that they cannot influence, right? So this determines the state of the world, so this is the state variables. And this is in our model, the capital stock, right? This is what we basically inherit from the last period, right? I mean, we can influence the capital stock, but only for the next period, right? If we invest, the capital stock increases, but this is only relevant for production, for output in the next period. So in this given period, the capital stock is predetermined, it's a state, right? And the second thing is our productivity level, right? This is also something which is the stochastic process, right? We wake up in the morning and then we see what is the current level of productivity, right? We cannot influence that by our actions in period T, actually. Actually, here productivity is completely exogenous. We cannot influence it at all, right? This is different with capital, but we get there next. Right? But both of these variables are states. What about the other variables in the model? Actually, all of them will be control variables plus the prices, right? I mean, prices here, prices matter, but not for the solution of the model, right? But what I'm actually talking about is like these actual variables, like consumption and labor, and this is then kind of the non-states. So this is what we call the control variables, right? And again, here you see the wording, right? This is what the agents in the model, which would actually also include the firms, right? In case you have firms that actually do something, in our model they are not doing much, but in principle would also include the firms, that they affect, right? So this is, for example, consumption and labor in our little model, right? So I wake up in the morning, I see the level of capital, I see the productivity level, and then I decide about consumption and labor. Okay. And this is how we have to solve for what we need for the solution. So just so that you've heard this once, right? So basically what we're entering here a bit is exactly this one, what is crucial whenever you work with macro models. How do we solve dynamic models? A different approach to do this is what we call dynamic programming. Have you ever heard this? Probably not, so now you've heard it once. So what is dynamic programming? Again, this is math, right? This is not so much economics, but it's one of these things that we're doing in economics like crazy, right? Because whenever you have dynamic models, you need ways to solve dynamic models, and the most prominent way is this, right? The advantage of dynamic programming is that the method of undetermined coefficients is basically a special case that works for these very small problems. Dynamic programming also works for larger problems. But it's also a bit more complicated and very often not doable in analytic ways, but only numerically. But that's for the future. I actually talk about this in case you find this interesting. I talk about this in my quantitative macro course in summer. Right? So then we'll do this, we'll do examples of this. Okay, so let me now show you what I mean by my solution from the perspective of the method of undetermined coefficients. So what is that solution that I'm actually talking about? This is how the method of undetermined coefficients starts, right? So let's think about what the solution of the model actually looks like. What is it? Well, I just made this distinction between state and control, right? And this is crucial now, right? So the solution of the dynamic model maps the state variables, and in this case my capital stock and my productivity level, in exactly the control variables, right? So in these choices, C and N, right? So I take here as inputs on the right-hand side, what is these two things that I wake up with, capital stock and productivity, and then what falls out, right? What's the level of consumption? What's employment in this economy? But the point is, in equilibrium, right? So the way that I just presented you was basically, how do I, as a household, choose consumption? But that's not the full story here. It's not only the household decision, but it's households and firms coming together, plus all the market equilibrium, right? So in equilibrium, what will be consumption in this economy, right? Taking all the actions of all agents in this model together, right? That's what I want to know, right? Same for N, right? And maybe just to give you a bit of an interpretation, I will be talking for a long time about these eta coefficients in the following. So these eta coefficients, this is our undetermined coefficients, right? This is where the name of the method of undetermined coefficients come from. That's these etas. So what you see here is this eta coefficient is the one which is related to AT, right? In this equation 45, the equation for consumption. So this coefficient tells you if productivity goes up, by how much does consumption increase? Right? Think of this as a derivative, right? If you take equation 45 and you take the derivative of consumption with respect to productivity, this would just be this eta coefficient. Right? So it tells you exactly if productivity increases by 1%, by how much does consumption go up? Right? And if you have a number for that eta, if that coefficient is 2, you will know it's 2%. Right? So that's this thing we are looking for. Right? Okay. You can do the same for labor, right? But the point is, these equation 45 and 46 is not yet enough, right? This tells you something about the current values of consumption and labor in your economy, but what happens in the next period? And in the next period, you need to think about how do your states now evolve over time, right? So for these two equations here, I said this is all conditional on the states. So you need to know how these states behave, right? So how can we describe that? And this is where the dynamics now show up again, right? So today's capital, tomorrow's capital stock, will depend on today's capital stock plus productivity. And the productivity process will depend on the capital stock plus today's productivity, potentially, right? This is what we call the law of motions for the states, right? And this is here just defined very generally, right? But note that if you know what these etas are, right? So you would need to know every eta here, right? All of these, how many is it? 8 etas, right? Then your dynamic system here is completely described, right? If you have initial values, K0 and A0, you can compute current N, current C, and then you would use your law of motions here, you would compute future K, future A, and then you can compute future C, future M, and so on and so forth, and your whole system is solved, right? So this is what we are looking for, right? And the task now is, take your log linearized model, sorry, that was the wrong direction, take the log linearized model equations, right, so 44, 43, 41, 42, and see whether you find a way to bring that in this form. That's basically what you need to do, right? Or a different way of saying that is, find solution for these etas. Right? So this is basically the whole procedure of the method of undetermined coefficients is think about what your solution would look like, right? And I mean, I'm actually making a very strong statement here. Sorry, I have to say that once, right? I'm actually postulating here that the solution that we have is linear. Right? This makes sense because we started with a linear model, because we did the log linearization first, right? In case you would not have done that, guessing the linear solution would be a very heroic guess, I would say. Right? Here, it actually turns out to be a pretty good guess. But this is conditional on our whole model being linear. Right? Okay. And then what we will need to do is we will need to check whether we find solution for these E terms based on our model. And if we do, we've solved the model. Right? And here you have it. Make a guess for your model solution, and then verify that this guess is correct. Alright. This is the theory, basically what we want to do next. I will show you how to do this next after the break. Right? Okay.
Legen wir uns einmal die Hände auf die Schulter und wir rotieren in unserem Box alle zuerst nach links, von mir aus gesehen die andere Seite, aber links, genau. Und dann nach rechts. Und wieder links und rechts im Wechsel. Und wir versuchen jedes Mal ein kleines bisschen weiterzubringen. Nochmal links, rechts und wieder zur Mitte. Okay, dann nehmen wir einmal die Arme über den Kopf. Jetzt strengen wir uns 10 Sekunden ein bisschen an. Okay? 10 Sekunden mit den Händen so tun, als wenn wir Holz haben. Ja? Okay, so richtig schnell. 10, 9, 8, 7, mehr, 6, 5, 4, 3, 2, 1. Sehr gut. Okay, wir sind wach und haben uns ein bisschen betätigt. Sehr schön. Und nehmen die Arme dann nochmal nach vorne und schieben die Arme aus dem Schultergelenk nach vorne und wieder in die Schulter zurück. Genau, und vielleicht merkt ihr schon, wir nehmen dabei die Brustwirbelsäule mit, wir werden rund, wir strecken uns durch. Und nochmal Arme nach vorne, zurückziehen, aufrichten. Vorne einrunden, zurück und nach. 2 noch. Und dann die Arme einmal absenken und dann greifen wir mal uns rum. Wir nehmen uns sozusagen selber in den Arm und die Finger packen wir hier ein, aber die Schulterbänder. Und dann einmal das Kinn auf die Brust nehmen und den oberen Rücken ganz rund machen. Schulterblätter mit den Fingern so ein bisschen voneinander wegziehen. Und dann drehen wir die Bewegung um, indem wir uns nochmal in die Position öffnen, durchstrecken, Brust raus und vorne aufdehnen. Ja, wir halten uns noch einen Moment. Und schütteln dann die Arme nochmal aus. Sie kommen in der vorletzten Übung nochmal in den Kopf. Und Achtung, jetzt drücken wir den Kopf in die Hände, nicht umgekehrt. Wir drücken den Kopf in die Hände, wir spannen den Nacken an, um den Gang vor Brust locker zu lassen. Und nochmal, Kopf in die Hände drücken, anspannen, um zu entspannen. Nochmal, anspannen, locker lassen und 2 noch. Einmal anspannen, lösen und nochmal halten, halten, halten. Wir sind angespannt und wir sind entspannt. Sehr gut, da schütteln wir alles nochmal aus. Letzte Übung, einmal das Kinn auf die Brust nehmen. Wer möchte, schließt mal kurz die Augen. Gibt sich eine kurze Pause. Wir drehen dann einmal zur linken Schulter rüber mit dem Kinn auf die Brust. Und dann schauen wir einmal hoch zur Decke. Senken das Kinn wieder ab. Wir drehen nochmal ganz eng drehen. Nach rechts, wir gucken nochmal hoch. Kinn absenken, nach links drehen. Nach oben schauen. Und nach rechts drehen. Nach oben schauen und jeder noch einmal zu jeder Schulter. Und noch einmal zum Schluss zur Mitte. 2 tiefe Atemzüge nehmen. Und dann aufrichten, ausatmen und damit im Licht nochmal sehen, wünsche ich frohe Feiertage, einen guten Rutsch und wir sehen uns im neuen Jahr wieder. Danke.
break again. I hope. Questions? I bet there's many questions, but maybe let me just show you what I mean by what I talked about, right? By the way, this is really right. If you Google method of undetermined coefficients, this is how it works, right? This is basically what you find. So it sounds, I hope, relatively simple. Let me show you that it actually works in the context of our model, right? All right. So I want to do one more previous step before we really go towards solving for these meters. And I mean that you've already seen me doing this, right? But in particular for solving a model analytically, right? I mean that if you want to open your computer, it may not matter that much. But once you do it by hand, you really want to make sure that you're really just using the variables and the equations that you really need. So you basically want to make your model as small as possible, right? And here's one equation that we can actually very simply substitute out, which will spare us one variable, one equation, right? So instead of solving for 4 variables, 4 equations, we would just have to solve for 3, which is easier, right? So the thing that we can substitute out is this n, right? I mean, on this previous slide here, I still had it in 46, but the point with labor here in this economy is labor is completely flexibly adjusted in every period, and it also doesn't affect the future outcome, right? Nt plus 1 doesn't matter here, right? So we can very simply substitute that out. So basically, you have it on the slide here, I should just stay here instead of jumping, right? So basically what I did is just to take the model equations and basically what I did is just to take this equation 42 here, solve this for n, right? I mean, just write this thing here, and then you have nt hat equals something, right? From this equation here, right? And this is what I substitute then into the other equations, right? So for example, if you substitute then 41, you would need to write this here as nt plus 1 hat equals something, and then you can put that up there, right? That's all to do, right? And it's also showing up here, you would do the same thing here, right? So you would introduce basically these equations 42 and 41 and 43. And then what you get, it looks always a bit more, it becomes more ugly and uglier. So I apologize for just to say why I do this, right? This is why these equations, these 3 equations that you now have remaining, they become longer, right? Because we just substituted in for these n's, but it is still the same equations, right? Believe me, still is the same equations, right? It's just I have to make sure that you're not missing any parameters, right? But this is exactly what falls out. Right? Okay, so it's still I mean, this here is still our Euler equation, right? It looks, I admit, ugly now, but it still relates Ct to Ct plus 1, At plus 1, Kt plus 1, right? So that's still the same thing. So now, given that this whole thing becomes so ugly, I want to solve this analytically, which means basically by hand, right? I have it on the slide, so you don't have to write it down, it's all there, but it's basically done by hand now, right? So instead of always having to write these very long parameter terms, right, let's basically, what I do now is just to say, okay, this whole term here in front of the Ct plus 1 hat, in the following, I just call this here, I think alpha 1, is that correct? Yeah, here, right, I just call this alpha 1, right? But alpha 1 is this whole thing, right? Same here, so this is the thing in front of At plus 1 hat, so this is basically my alpha 3, right? And this here is my alpha 2, sorry for messing up the order, right? But it's just like you're collecting the parameters in front of these three variables here, right? I call them alpha 1, alpha 2, right? Which makes this ugly equation on the previous slide, again, look a bit more easy to handle, right? Right? Which, underlying this alpha 1 is this whole parameter thing, right? Plus the steady state. I do the same here, right? Also here I'm basically sorting all my parameters in front of my variables and call these things alpha 4, alpha 5, and alpha 6. Right? Same mechanism. Right? 51 is easy, right? So that one looks already pretty clean, right? That we can just like take as things. Okay. So now we've reduced the model to these three equations, right? 49, 55, 51. Right? So now I basically start the method of undetermined coefficients, right? We want to solve for these eters. But the point is, maybe before we start doing this, to note that actually one of these eters basically already falls out of our model. And this is the one for this productivity process, right? So if you look at this equation 51, this equation 51 is just an equation that just depends on itself, right? Productivity today just depends on productivity yesterday plus this exogenous shock. So productivity in this model is what we call exogenous, right? It's not affected by anything in the model, so no endogenous feedback, right? So about 51, we don't have to worry, right? Or in other words, this recursive law of motion for alpha hat is basically already given, right? Sorry for jumping, but let me once show you what I mean by this, right? So this equation here, right? This is the recursive law of motion for productivity. That guy I can basically write down immediately without doing anything, right? Because by the definition of the model, there is no effect of kt hat on future productivity, right? So this eta ak is 0. Maybe that's a better way to say it, right? Instead of just, we know this guy here is 0, right? Because productivity is exogenous, right? We also know what this here is. This is this coefficient rho, right? By construction of the model. Right? So 48, I've basically already solved for, right? That wasn't easy. Right? And this is just what I do here on the slide, right? Basically to tell you, just use this, right? I mean, you would use it in expectation, right? So maybe just to make that point once, right? So what's the expectation of this epsilon t? So why am I mean, basically what I do here, right, is to say the expectation of epsilon t plus 1 here has disappeared, right? Why has it disappeared?
Because we determined, or we said that with a mean of 0 and the variance of some positive value.
Exactly, right? So this is important, right? I mean, I'm using here that E of epsilon t is 0, right? So this thing is well-defined, has a mean of 0, it also has a well-defined variance. It does not have any covariance, right? If it would have a non-zero covariance with productivity or with, I don't know, capital or whatever, you couldn't do this, right? But here, it's just this exogenous thing, so we can just get rid of this. So because this here is 0, here it falls out, right? Okay. So what we now actually need to solve for is these two guys, right? So n is gone because I've substituted n out of the model, but what we managed to solve for is this policy function. This will actually be a policy function at some point for consumption, and the law of motion for capital. Right? That's what we have to solve. The law of motion for productivity we already have, the guy for n we have substituted out, right? So this is what we need. Okay. And this is basically all you need to do now, right? So the idea of the method of undetermined coefficients is we have guessed our solutions, right? We have guessed that this solution here exists and that these parameters here exist, right? So then let's just use it, right? So basically what we do is say, okay, then I substitute this equation 53 and 54 and I use that in my model equations in 49 and 50 to get rid of any variable in this equations that is not a state. Right? Or in other words, use 53 and 55 to rewrite 49 and 50 just in terms of AT and KT. Right? So maybe let me show you once how I do this. Right? So basically, you can start here on the left hand side, right? 49 starts with the CT. Right? CT is not a state variable. right? The state variables in my economy are KT and AT. Right? CT is not. Now to solve this, I want to reduce the whole thing just to states. So let's get rid of CT, and I can get rid of CT by using 53, right? Because 53 tells me that CT equals this guy here, right? So I insert that here basically on the left-hand side and just say, okay, this equals e to the ck, kt hat plus e to ca at hat, right? And then instead of having ct hat here, we have this here on the left-hand side. Right? And that's the advantage now, right? Because I'm using this policy function. This just depends on the states. Right? So I replaced the control variable with something that just depends on states. Right? I can do this for the ct here. I can also do this for the ct plus 1 on the right-hand side. How do I do this? I mean, I do not have an equation here telling me ct plus 1 equals, right?
Maybe plug into the ct hat function for kt hat, kt plus 1.
Exactly, right?
Same thing for at, which is...
Yeah, we can do that in a second, exactly. But that's the idea, right? So for 53 holds in period t, it will also hold in period t plus 1. So you can write 53 just as ct plus 1 hat equals e to ck kt plus 1 hat plus e to ca at plus 1 hat, right? This is just, that's it, right? But now you have, this is now a function of kt plus 1 and at plus 1. This is also not directly what you want to have, because you want to have everything in terms of kt and at, not of kt plus 1 and at plus 1. So now what you would do is say, okay, kt plus 1, I can replace with 54, right? So according to 54, kt plus 1 is just equal to this guy, right? So I would introduce that here. And for at plus 1, this is what you were already suggesting, right? You can use 52, right? At plus 1 equals rho times at. So for that here, you can insert rho times at hat, right? And then you get for ct plus 1 something which also just depends on kt and at, right? And this is what you would then introduce here. So I'm doing lots of steps here now, right, which you probably will not see immediately, but believe me, this works, right? And I mean, you can also, I mean, maybe that's, I know I say that, you will probably not do it, but take my word, if you sit down at home and do the math, right? Take this equation, insert that there, do this step by step, right? At some point, you'll get exactly this equation, right? This, I mean, the equation is correct. Actually, a computer has checked that. So I know that's right. So this, I mean, but that's what I mean by solving by hand, right? I mean, this here is, I mean, I'm taking that seriously here, right? You would really like take all these equations, insert one into the other, and then rewrite, I mean, let's start with 49, right? Just 49 just in terms of kt and at hat, right? So that was the whole idea, right? Here you have a t plus 1 here, you have a t plus 1 here, you have a t plus 1 here, right? Here you just have kt and at, right? That's the whole purpose. Get rid of these. But this is getting rid of these, I mean, costs us something, right? What it costs us is that we're introducing all these eters, right? So this equation obviously looks again very ugly. So we have now not only these alphas flying around, but we also now have these eters flying around, right? Okay, but it works. Now do the same thing for equation 50. For 50 it's admittedly a bit easier, right? Because for 50, kt plus 1 you can replace immediately by 54. Kt on the right hand side can just stay, this is already a state in t. At can just stay, this is already the state in t. For ct you can use 53 directly, right? So this is basically, this is relatively easy. that one and that one here, and then you have it, and you get this equation here, and I mean, you already see it, that one is a bit shorter, right? It looks a bit nicer to deal with, right? But again, you now have these e's flying around in that equation. Okay. So was that helpful now? Maybe. The thing is, these two equations on the top, we can now actually solve. Why? Well, because there's a kt and at, which is our unknowns, right? Two unknowns, two equations. Right? Kt, at, two equations. That's looking good, right? Is that something you can solve? Yes, you can, right? So a different way to look at this is to say, both of these equations, I mean, I've written them in such a way that they equal 0, right? So if I want these equations here to equal 0, this means that these Hubble parameter parentheses that I have here, this guy, for example, will have to equal 0, right? Also, this guy here will have to equal 0, same here. 0, 0, right? Why? Well, because, I mean, my capital stock and my productivity level will not generally be 0, right? I mean, it can also be that at some point they will also be 0, but we are looking here for general equations, general solutions that holds for every period t. Why would I restrict my model to have in every period a 0 capital stock? This wouldn't make any sense, right? So having kt and at equal 0 doesn't make any sense. So if I want this equation to be equal to 0, I have to set these parameter things here equal to 0, right? Same for the first equation. Right? So looking at it that way, this implies that these 4 terms, right? This is just the first term that you've seen out there. This guy has to equal 0. This guy has to equal 0. This guy has to equal 0, and this guy has to equal 0. So this is just these 4 conditions here. And this is now actually very nice, right? Because here, I mean, you can count the unknowns, right? I mean, the important thing to see is we know what the alphas are, we know what this rho is, right? Alpha and rho is parameters of my model, right? This is stuff I can control, right? I mean, this is my model, I've written that down, right? So this is stuff I know. What I do not know is the eters. But the whole point of the method of undetermined coefficients was, do we find solutions for the eters? And we are now actually very close to finding a solution, right? Because you now have here just these 4 unknowns, right? Eta ck, eta kk, eta ka, and eta ca. This is 4 eters, and we have 4 conditions that have to hold. So 4 unknowns, 4 equations, something we can solve. Right? And this is really just what I do on the next slide, right? So this is basically math from school, or I don't know, right? So all you need to do, I mean, there's basically different ways to start here. I think how I did it on the slide is to say, take your equation 57, and let's say you solve equation 57 for eta ck, right? Rewrite that guy, then you have eta ck equals eta kk minus alpha 4 over alpha 6, right? Is that correct? I think so, yeah. Right? So that's basically equation 57 rewritten, right? Let's solve for eta ck. Right? And now take this here and insert that here. And insert that here. Right? Why does it help? Because this thing just depends on eta kk, right? And then you have one equation in eta kk. So one equation, one parameter. So then you can solve for this parameter, right? If you do this, I mean, what you will see, you have an eta kk here, and you're multiplying that with an eta kk here. You get here an eta kk squared, right, in that equation. Which means you need a quadratic form to solve it. But again, I mean, this, I would say, right, school math, right? How do you solve this quadratic form? just write it down, use this, what we call this PQ formula, right? Solve it. I mean, as you maybe know from school, right? If you have a quadratic form, you typically have two solutions, one positive, one negative. This is exactly what you have here too, right? But it's interesting, right? And I mean, again, right, with larger models, or even here, right? Obviously, normally we don't do this by hand, right? But here, what I want to show you, you can actually do it by hand, right? I mean, it's not like this is, it takes a while, I admit that, right? Obviously, computers are much faster at that, but it's doable, right? And I mean, in the end, the computers just do what we tell them. It's not AI, but so far, right? Right? So I want you to understand what's going on there, right? And this is where it's coming from. Right? So here now you have a solution for e to kk. Actually, you have two, right? Because it is this quadratic form, right? So what do? Here in this setting, I mean, this is e to kk that we're solving for, right? And now again starts a bit of the economics. So what is e to kk? E to is this persistence in the capital stock, right? E to kk tells you if my capital stock increases today, what's the effect on tomorrow's capital stock, right? So it has an economic interpretation. And this is why it makes sense here to choose the solution for e to kk, which is smaller than 1, right? Because this is going to imply that our model is actually always returning to a steady state. I mean, you can talk about it for ages. You can actually formally prove this. I'm not doing all of this. Just to say this stuff here could be done here now. But maybe just remember the discussion that we were having at the very beginning when I talked about the solar model or the neoclassical growth model. Whenever you have a steady state, do you have a unique steady state, or maybe you do not have a steady state at all, right? This is basically a similar discussion here, right? You need to make sure that your model does have a well-behaved, dynamic solution, steady state, right? And this is basically what we're doing here. Right? You're picking basically the solution that makes sense for us, right? Okay. And I mean, but note that this is really, I mean, this is, on the right-hand side, you just have alphas here, right? This term looks super ugly, I know, right? I mean, you have this root here, squared, whatever, right? But these alphas just depend on your model formulas, right? So there's the discount factor involved, there's this alpha of the Cobb-Douglas involved. This is what's showing up in your model, right? And this is what determines your E to K. Yeah, I mean, obviously with eta kk we're not yet done. You need to find solutions for all 4 of these eters, but I mean, if you have the e to kk, you can choose to solve for the e to ck immediately from that guy, right? Basically from equation 57, and also the other 2 fall out, right? Once you have e to kk and e to ck, you can solve that guy, and then you can also solve that one, right? And then you get a solution for these 4 eters. So there's the other. And then you have it. Questions? I know that this is always a bit hard to, I don't know, digest. Maybe that might have excellent. So before we talk about the calibration, I mean, we do this at some other point, but let me show you what I actually mean by a solution here, because I know this is always a bit abstract, right? So this Excel file, I've already uploaded that. This is an Excel file that solves the RBC model, right? I mean, I just said repeatedly, our computers can do this. For that, you don't need any advanced software. Actually, Excel can do it. This is an Excel file which is doing it, right? This is why I like presenting it that way, because it's in the end it's not simple. But once you have it, you can actually simply do it in Excel, right? Okay. But I just wanted to show you these numbers here once, right? So what I do in this Excel file scale, and I mean, I will talk about later how we choose these parameters, right? But here I choose numbers for all my model parameters, right? Alpha, beta, delta, phi, rho, right? So phi is this coefficient on labor supply, the utility function. Rho is this persistence we've talked about, delta is the depreciation rate, and so on and so forth, right? So I actually pick numbers, right? And what that means is that we can then compute, first of all, these alphas, right? And I hope you can read this, but note that these underlying formulas here in Excel, right? This is the formulas that I just gave you on my slides, right? I'm really just like implementing one-to-one what we have on the slides in Excel, right? So if you see here, this 1 minus delta, and then you have the steady state of output over capital, right? This should be exactly this output equation that we had a couple of slides ago, right? Basically, here, right? So this is one-to-one, well, this is where this is coming from, right? So I'm not making that up, but this is actually representing this, right? So I'm computing the outputs here. And now what I do, I compute the eters, right? And I mean, again, these formulas look pretty ugly. That's why you typically don't do it in Excel, because actually typing that in is a pain, but it works, right? So if you put this in here, right, you can actually compute these eters. And that's what I mean by a solution, right? These things are just numbers, right? So it turns out here that this eta kk is 0.95, right? So we can solve this, right? That's what I mean by this, right? Okay. And why is this now important that we solve this? Well, and I mean, that's basically this other slide that I have here. Now think about a situation where in your model something is happening, right? And I mean, the stochastic process that we have in this model is this productivity guy. So there's productivity increasing, right? So let's say we have a period 0, there's a shock to productivity, right? Epsilon 0 on this slide here is now larger than 0, so it's positive, there's something happening, right? So this feeds directly into a higher level of productivity in period 0, right? And now you can look at your eters and actually compute what does that mean for consumption, what does it mean for the capital stock, right? And for that, you really just need these eters, right? So eta CA is the parameter on productivity, right? So let's say productivity goes up by 1. Just make it very simple, right? Productivity goes up by 1. A0 would go up by 1. So this is a deviation from steady state, so by 1%, right? So then eta CA will tell you, so then on impact, if productivity goes up by 1%, by how many percent does consumption go up? And I mean, in our example here, eta CA is, let's make it correct, where is eta C? Sorry, I'm calling that Z, that's not nice, but this is eta CA, right? Is around 0.4, right? So the interpretation would be if productivity increases by 1%, consumption increases by 0.4%. Right? This is what the model gives you. Right? And this is determined by this eta, and this is why I was talking about this eta for such a long time. Right? You can also ask what happens to capital, right? This is just the eta below, right? This is either K, A, or Z, which is 0.1, right? Capital is 0.1. And this is exactly what, like, us macro people keep plotting the whole time, right? So now what we do, this was just the impact response, right? So now we say this process is autoregressive, right? If there's something happening today, we know it also matters for tomorrow. And in our model here, we can compute exactly what happens tomorrow, right? We can then compute what does that mean for the capital stock tomorrow, what does it mean for the level of productivity tomorrow, right? Once we have that, we can then compute the level of consumption tomorrow and the capital stock in the next period, right? And again, I mean, in an Excel file, I just have to put all that in. I just have to compute this, right? All these equations are there now, right? And this is then these figures that you always see in macro talks, right? This is our impulse responses, right? So there you see then over time, how does the capital stock consumption, yeah, and I'm also plotting productivity here, how does that behave, right? And I mean, just to say that the impact here is really just this Ito coefficient, right? So the impact, I mean, the first one, right? The first responses here, this is really just the Ito coefficients that we just computed, right? This is where they come from. And this gives you, I mean, the interpretation, right? Let's say consumption increases by about 0.4% if productivity increases by 1%. This is the aggregate response of consumption that you see in your economy, taken together household responses, firm responses, market clearing, right? So this is an equilibrium response, right? So all these people are acting at the same time, and then this thing here tells you what does it mean now, right? All this coming together, what does that give me, right? This is what's happening. Okay, so this is basically this. So I mean, I think Maria will also work a bit with this Excel file. I mean, but I've already uploaded this because I just find it always very helpful. Maybe you do too, right? Because you can actually really, hopefully, see a bit. I mean, on these slides you have these ugly equations, right? But like where they go and what that actually does in the end, right? Questions?
So I thought that these hat variables are already the percentage changes. So it seems as if it's like the same thing twice. For like eta ck and k0 hat. Like what is what? Like if k0 hat is a 1% change from the or deviation from the steady state, and isn't that already the magnitude of the effect?
So let's say k0 hat were 2, right? Then you would say capital is 2% higher compared to steady state.
Yeah.
Right? And now let's say e to kk is, I don't know, 0.5, right? So then that would mean that then the future capital stock, k1, would just be, I mean, conditional on that thing here being 0. But I say 2, then that would just be 1, right? So then you would in the next period have a 1% higher capital stock compared to steady state. Does that make sense?
Yeah. So these are the etas are the weighting of factors that.
So in a way, the etas, you can think about etas maybe as derivatives, right? I mean, what's the easiest? This one is yes, maybe easier, right? So let's say alpha a. So how is the capital stock change? Future capital stock change if the deviation from steady state increases, right? And that would be e to ka, right? But you're right, it's the change in the deviation from steady state, that's true, right? So we typically start with a setting where the deviation from steady state is 0, right? Because we typically start in the steady state. And then you were to say, okay, now this thing goes up from 0 to 1, right? And then you would have a change of 1, and then you have exactly this e to ka. Other questions? All right. So now I'm in this Excel, I've already just said, I'm using numbers for all my parameters now, right? And I mean, there's a reason why I do this. In principle, you don't have to do it, right? If your model would be a bit smaller, and there's also special cases you could write down, where you could maybe even make like analytic statements, right? So let's say, so the problem in this model here is that this guy here is super ugly, right? Basically, this equation here prevents me from making statements like, I don't know, let's say we change the, whatever formula you want to change, depreciation rate, right? And I would want to know how does e to the kk change if we increase delta or something, right? I mean, that was, for example, things, or like in the phase diagram, we changed beta, maybe it's the beta again, because that's what we did earlier, right? So in the phase diagram, we had an exercise where we asked, how does the model change, or the model equilibrium change, if we increase the discount factor, right? And I mean, here I want to ask the same questions, right? I want to ask how, like, does the model respond if I change certain settings, certain parameters, right? And let's say this e to kk would be a bit nicer in these alphas too, right? You could maybe do an analytic derivative, right? I mean, why not, right? I could look at these alphas as just some functions of parameters. Maybe I'm actually able to say whether this thing here is positive or negative, let's say, right? That's basically what we did in the phase diagram, right? I made this figure and then I kind of showed you that for whatever reason these model responses are positive or negative, and this is why we shifted the curves in certain directions, right? Here I don't really see that anymore, right? So that's basically the reason why we say, if I'm not seeing that analytically, right, I have to compute it with numbers, right? So this is what we do here, right? So we basically put in parameter values, right? And this is what we call calibration, right? This is just this whole thing, right? We calibrate a model. By that, all we mean is we take the model parameters and we assign actual numbers to these parameters, right? And I mean, there's this practical point, right? Because otherwise we're maybe not even able to make any statements anymore, right? There's also a big advantage because you can then actually make these statements like productivity goes up by 1%. How much does consumption change, right? 0.4, right? This was the number that I already gave you, right? And I mean, this actually also allows you at some point to compare that to data, right? I mean, this is also something that I do in my quantitative macro course, right? So then you will basically take data evidence, put that exactly next to your model evidence, and then you can really compare one to the other. This is also something that, based on just a qualitative analysis of your model, you can never do, right? So this is why, like, this calibration has been, I mean, this is what we're doing ever since these guys came up with that, right? I mean, this goes back to Kipling and Preston. This is also one of the reasons why this RBC model is so prominent, because this was proposed in the context of the RBC model, right? I mean, now we're doing this in the settings of millions of models, right? But this is where it's coming from, right? So they basically proposed this, right? Exactly with this idea in mind. You want to be able to compare your model to the data, right? And there's kind of these three rules that we typically try to have in mind, right? So you need to make an argument why you set your parameters in a certain way, right? So far I've thrown some numbers on you, but just using some numbers is not really scientific, right? If you want to make a clear statement why we use what number, right? And this is basically the art of calibration, right? Find a good story for, like, to justify the numbers that you actually use. And there's like these three gold standards, if you want, right? The first one is try to use as much microdata as you can, because basically the idea is you want to stay away from using the data that you actually want to explain, right? Because if you put in the data that you want it to explain, and then your model explains it, maybe that's not really too surprising, right? So here a bit of the idea is use data which is outside of your model to calibrate your parameters, and then see whether you can actually explain the data that you've not used for calibration, right? Okay, so this is why we typically use microdata. So for example, this Frisch elasticity parameter, this phi, people try to estimate that for decades, right? We try to estimate this wage elasticity in microdata, and the problem always is there's millions of studies that do it. Every study finds a different number, and then you have to pick one, but that's different. That's the problems that are coming out then, right? But that's the general idea, right? Okay. We also use a long-run trend data. So what do I mean by that? Think about these labor shares, right? So I've talked about the Cobb-Douglas, right? That this alpha in the Cobb-Douglas matches the labor share. This is typically why we set this alpha to 2/3, right? That's just a very simple idea, right? And for this productivity process, which is crucial in an RBC model, we typically do this solo stuff, right? I've talked about the solo growth accounting, where you compute this TFP process, total factor productivity, right? Or the solo residuals, as we sometimes call them. So then you would also say, take that from the data and then match it. Right? There's some more stuff that you need to do. Typically, we think about the steady states, right? So if you, for example, take the steady state of your Euler equation, right? This is the equation up there. Compute the steady state of your Euler equation. This is just this here, and the big advantage of the Euler equation is the steady state is very simple, because this guy and this guy just cancel, right? Once they're the same, they're just canceling, right? And then you have this equation falling out, right? So you see a direct relationship of the discount factor, the depreciation rate, and the real interest rate. And then what we typically do is we have kind of an idea on what like our long run real interest rates are in an economy. Again, we can basically use data on that. And this is then how you, for example, match the discount factor and the depreciation rate. Typically jointly with the discount factor, typically falls out of the idea up there, right? I mean, if you take the law of motion for the capital stock, the discount factor is directly related to the level of investment over capital in your economy. Again, this is something you can compute from data, right? Take national accounts data, right? How much investment do you have in a year? What's the capital stock of your economy? We can compute this, right? And this is the numbers that we then typically put into our models, right? So let me just give you an example. So typical parameter for delta would be like the 0.025. This is what you typically see, because this then implies that you have an like I over output in this case of 25%, 24%. Right? How much do we invest of GDP? It's around 24%. Which also determines then the level of consumption of a GDP to be 75%, right? And this is like things that you seem to be correct in long run data, and this is why we're putting that in, right? You have the real interest rate, which basically determines the discount factor once you have the depreciation rate fixed out, right? This labor supply elasticity, because we don't know what it is, just set it to 1, right? That's what we do. But I mean, I actually show you later, and I mean, that's also the kind of the beauty of this, right? Obviously, this is stuff which is very easy to change, right? This is something you can even already check in this Excel, right? If you don't like 1, make that number 2 and see how your model changes, right? So that's very easy to do. Good. I should probably stop here. Questions? Good. So now you've seen, I think, that was a lot today, right? The important thing I want you to understand is this method of management efficient, which also implies a bit understanding what I actually mean by solving a model and by a model solution, right? And I'm aware that this is not trivial, so maybe it also takes some time, right, to go over this again, because I believe that it is important. And from next week, Wednesday, right, we'll actually use this, right, and then talk about what this actually all means economically, right? I mean, this follows next week. Okay, see you guys later. Right, and this again for your planning, so not next week Thursday, that is cancelled, but on next week Wednesday, I will be here in this normal tutorial session.